Across the featureless expanse of the Southern Ocean, thousands of miles from any visible shoreline, a gray-headed albatross cuts through dense fog without a single flapping of its narrow 3-meter wingspan. The air temperature hovers near freezing, and beneath the churning dark water lies an oceanic abyss that stretches downward for thousands of meters into ink-black silence. Standard navigation theory insists that pelagic birds rely on visual landmarks, celestial tracking, or subtle chemical plumes drifting along the sea surface. Yet in zero visibility fog, under a blank and sunless sky, this solitary traveler tracks a precise trajectory across the open ocean toward a microscopic feeding ground. For decades, oceanographers believed the open sea was a silent void, a featureless desert where animals drifted on random currents. But modern bioacoustics reveals a far complex reality. The atmosphere above the oceans is saturated with an invisible, low-frequency soundscape known as infrasound. Generated by the continuous collision of massive, deep-water ocean swells, these acoustic waves travel thousands of kilometers at frequencies far below the threshold of human hearing. Where traditional biology saw a bird drifting blindly through space, neuroethology is uncovering a sophisticated biological receiver, decoding an invisible map written in sound. Deep within the inner ear structure of the albatross lies a highly specialized organ capable of detecting micro-barometric shifts and acoustic vibrations oscillating at frequencies below 20 Hz. While a human observer, standing on the deck of a research vessel, hears only the immediate crash of wind against canvas, the albatross processes a dynamic, three-dimensional sonic blueprint of the planet. Every distant storms-driven wave vector, every deep ocean shelf break, and every subterranean trench produces a distinct acoustic fingerprint that reverberates across the marine boundary layer. Consider the mechanics of dynamic soaring. The bird glides through steep incline angles, plunging into the low-speed wind troughs created by ocean waves before climbing into high-speed winds above. This perpetual flight engine requires microsecond adjustments in wing tension and body mass distribution. Yet researchers tracking these birds with miniature GPS units discovered something extraordinary. Long before an albatross reaches a rich upwelling zone where cold, nutrient-dense water rises from the seabed, it executes a sharp, deliberate course correction. The shift occurs far beyond the range of olfactory detection, defying every classical model of seabird foraging. The explanation lies in how sound bends through atmospheric layers. Infrasonic waves generated by massive coastal surf breaks or oceanic ridges refract off the atmosphere, creating acoustic landscapes that remain stable across hundreds of miles. To a creature equipped with specialized atmospheric pressure sensitivity, the open ocean is not quiet. It is a resounding labyrinth of acoustic peaks, valleys, and corridors. The bird does not simply fly, it navigates an invisible sensory topography where geographic location is continuously calibrated against sound. In controlled field tests using spatial tracking and acoustic array mapping, marine biologists map the flight paths of breeding pairs against real-time infrasound distributions across the Pacific Basin. The correlation was undeniable. The birds were actively avoiding regions of acoustic silence and channeling their long-range movements through high-energy sound corridors. When a deep ocean storm thousands of miles away alters the wave structure, the albatross detects the shift within hours, adjusting its transoceanic transit to intercept the precise boundary where acoustic gradients signal high prey density. This sensory processing demands enormous neural allocation. Rather than operating on simple instinct, the avian brain functions as a real-time signal processor, filtering ambient surface noise from low-frequency standing waves. As the albatross skims inches above the whitecaps, its sensory organs register subtle pressure differentials across each wingtip. The bird measures the phase shifts of incoming acoustic waves, comparing the arrival time between its left and right ears to triangulated distant geographical features with startling precision. The mystery deepens when examining night flights. Under absolute darkness, with heavy cloud cover blocking all starlight, an albatross can locate an isolated island nursery measuring less than 5 kilometers across, hidden in millions of square kilometers of empty water. It hits the landing site without deceleration or hesitation, The flight path is a straight, relentless line drawn across an unseen map. What appears to human eyes as an featureless horizon is, to the albatross, an intricate web of acoustic markers guiding it across the globe. The key to understanding this oceanic architecture lies in the petrels and albatrosses' anterior olfactory bulb and the specialized mechanoreceptors embedded deep within their nasal passages and inner ear canal. For decades, ornithologists viewed these sensory systems as isolated tools, one for smelling decaying fish fat, the other for basic equilibrium. Yet neurobiological imaging reveals a complex sensory integration center where low-frequency sound maps, barometric gradient readings, and trace odor plumes merge into a unified cognitive model. As wind shears hit a wave crest at 40 knots, creating localized acoustic turbulence, the albatross reads the resulting pressure variation across its skull like a pilot reading a complex flight display. This internal acoustic mapping system exposes the deep flaw in traditional animal behavioral science. Early field models assumed pelagic birds simply wandered the vast south polar currents at random until they visually sighted a surface-dwelling squid or a floating whale carcass. But systematic telemetry data, collected across thousands of flight miles, proves the opposite. Albatrosses fly along precise, repeating highways carved into the marine boundary layer. These invisible transit corridors correspond directly to regional acoustic channels where deep ocean waves reverberate against continental shelves thousands of miles away. Consider the acoustic shock wave generated by a subsea earthquake or a heavy polar storm front moving across the Antarctic circumpolar current. Long before surface swells arrive, a pulse of low-frequency infrasound sweeps through the atmosphere at 340 meters per second. The albatross detects this acoustic wave front instantly. To the bird, the sudden shift in the low-frequency background register signals a dramatic change in ocean turbulence, hinting at upwelling currents that force vast shoals of lanternfish and ocean squids toward the surface. The bird pivots across a narrow wing axis, leaning into the crosswind, using the storm's acoustic footprint as a beacon toward its next meal. This spatial intelligence relies on dynamic memory frameworks that rival the most sophisticated animal cognition ever recorded. The avian brain does not merely register sound in real time, it maintains a long-term, dynamic memory bank of regional soundscapes. An adult albatross, after 40 years of continuous flight across millions of square ocean miles, carries a complex, evolving acoustic atlas of the entire southern hemisphere. It remembers the precise low-frequency resonance of every major trench, shallow reef, and coastal cliff line, continuously updating this internal database as ocean floor topography and wave dynamics shift over time. When the bird approaches its breeding colony on an isolated volcanic rock buried in dense sea fog, this mental atlas takes precedence over sight. While human instruments struggle against high winds and zero visibility, the albatross interprets the unique acoustic shadow cast by the island's steep basalt cliffs against the incoming swell. The island emits a distinct infrasonic profile, a low-frequency hum produced as massive ocean waves smash against subterranean rock formations. The albatross homes in on this localized acoustic node, dropping out of the gale-force winds to land precisely beside its mate on a mud-packed nest. This continuous stream of acoustic and spatial data shatters the outdated notion that bird brains are simple instinct engines driven by immediate stimuli. What we observe in the long-distance flight of the albatross is a continuous process of spatial problem-solving, environmental data processing, and predictive navigation. The bird calculates its trajectory by cross-referencing incoming sound waves, atmospheric pressure changes, and wind resistance against a lifetime of stored spatial data. As human industry expands into the high seas, this delicate acoustic world faces unprecedented disruption. Massive container ships, seismic surveying air guns, and offshore wind arrays flood the ocean surface with low-frequency noise pollution. This acoustic clutter masks the natural infrasonic signals that pelagic birds have relied on for millions of years. Understanding the deep-sea navigator's acoustic mind is no longer just a quest to unlock the mysteries of avian intelligence. It is a critical race to map and protect an invisible, silent realm before the soundscapes that guide these extraordinary oceanic travelers are lost forever beneath the noise of the modern world.